Okay, so let's try to solve this problem number 63, unique first 2. The problem says that you are given an m into n integer array grid. There is a robot initially located at the top left corner, grid 0, 0. So over here, it is located at top left corner. The robot tries to move to the bottom right corner, grid m minus 1, n minus 1. The robot can only move either down or right at any point in time, either down or right at any point in time, and obstacle are marked as 1 or 0. So there is an obstacle you can see, so this will mark as 1, and if there is space it will be 0. A path that the robot takes cannot include any square that is an obstacle. Return the number of possible unique paths that the robot can take to reach the bottom right corner. So we need to return the number of possible unique paths. Again, this number of possible unique paths that the robot can take to reach the bottom right corner. And we can see these keywords, number of possible unique paths. Okay, the test cases are generated so that the answer will be less than or equal to 2 into 10 to the power 9. Okay, constant has been mentioned as m is equal to obstacle grid dot length, n is equal to obstacle grid I dot length, m greater than is equal to 1, n less than is equal to 100, and obstacle grid ij can be either 0 or 1. I would highly recommend to solve the problem unique paths, which is problem number 62, before solving this problem unique paths 2. Okay, and I also highly recommend to watch my previous video unique paths. It has a detailed explanation about how we can approach first with recursion, and then how we can optimize with dynamic programming. As we already discussed the intuition behind this problem, I will directly move towards the approach, how we can approach to this problem. Okay, so let's discuss the approach now. Okay, in this problem we just need to tweak few base cases. So I'll take a function f which will accept 4 parameters I, j, m is the size of the row size, and n is the column size, m, n, and the obstacle grid. Okay, so first base case is if I greater than m minus 1, so we reached outer boundary. Okay, I greater than m minus 1 or j greater than n minus 1, or so this is 1, or obstacle grid we found in 1 in the obstacle grid. So in that case obstacle grid of ij is equal to 1, then we will simply return 0. Okay, so first base case is done. Okay, now this problem says that we need to return the count, we need to return the number of possible paths to reach the bottom right corner, reach to the destination, right? So we need to return a count, numeric value, like we need to return a value, not a boolean one, like whether boolean value in the sense like this problem does not say that whether we can reach to the destination. This problem says that we need to find the number of paths, so we need to return a number. Okay, so in this case if we'll put a case over here, so if I is equal to, if we have reached the destination, so if I is equal to m minus 1 and m minus 1 and j is equal to n minus 1, then simply return 1. Okay, next what we'll do, we'll at this they will simply call the same will simply call this function recursively while moving down or right. Okay, so return f of I plus 1 comma j comma m comma n comma obstacle grid plus, so we need to return the count. So in that case we need to do an addition over here. So whatever the options we are taking, so this is just to move down, and another we need to move right. So in that case, f of I comma j plus 1 comma m n obstacle grid. Okay, so if we do this, I think we'll get our answer, but for this time complexity will be exponential. So time complexity will be 2 to the power m plus n, and space complexity would be O of m plus n minus 2. Okay, like we have seen in our previous problem, right? So you need to optimize this, right? So in this case, I mean, if we draw the recursion tree over here, again we'll find some overlapping subproblems. So if we have overlapping subproblem, then we can optimize with dynamic programming. So first we will take the recursion with memoization approach, which is called top-down dynamic programming, and then we'll look for the tabulation, which is also called bottom-up dynamic programming. Okay, so let's look at the top-down dynamic programming now. So it is nothing but recursion plus memoization. Okay, so we'll take a dp for this. We'll take a dp of size m into n. Okay, and initialize with -1. Okay, so we'll copy the same function if I j m n obstacle grid. Okay, and we'll copy the base case. So if you are out of boundary, if I greater than m minus 1 or j greater than n minus 1, or we found 1 in the obstacle grid, we found a stone in the obstacle grid. So obstacle grid ij is equal to 1, then return 0. Okay, so this is done. Okay, then if we reach the destination, so if I is equal to m minus 1 and j is equal to n minus 1, return 1, we got a path. Okay, so this is done. Now if we already pre-computed the value for I and j, then we can simply return if dp of I forgot to pass the dp over here. So obstacle grid comma obstacle grid comma dp. So if dp of ij not is equal to -1, return 1. Okay, this is done. Next, what will store the value. So this we referred the we have referred the memoized value. Now we'll store the value of ij into our we'll memorize the value for ij. Okay, so basically what we'll do, dp of ij is equal to, so return dp of ij is equal to f of I plus 1 comma j comma m into n comma obstacle grid comma dp. So this is to move down, and another one is to move right, plus f of I comma j plus 1 comma m comma n obstacle grid comma dp. Okay, so if we do this, then what will be the time complexity? So time complexity would be O of m into n. Okay, space complexity would be we are taking a dp of size m into n, so we will have m into n, plus we will be having a recursive or auxiliary stack space of m plus n minus 2. So this is for aux. Okay, and this is for dp. Okay, dp table or dp to the dp array. Okay, okay, so we optimized using recursion and memoization, which is top down dynamic programming. Okay, now we'll look for tabulation. Okay, tabulation or bottom up TP. Okay, okay, so okay, first we'll get the row count and column count. Okay, column length and the row length. Okay, so m is equal to obstacle grid dot length. So this will return number of rows. Okay, and then we'll get the column length as well, number of columns as well. So obstacle grid 0 dot length. Okay, now so if in the initial position, right, so in the first cell, so if in the first cell if this is 1. Okay, so in the first cell if this is 1, so then we cannot move to any other position, so we cannot move the rest direction, right? So basically this is our stop position only, so we cannot move to any other direction. Okay, so you can say if obstacle grid 0 is equal to 1, then if obstacle grid 0 is equal to 1, then we can return 0. Okay, so this is done. Okay, now we need to declare a tabulation we are doing, right? So we need to declare a dp table over here. So in this case the changing parameters are m and n, so we need to declare a 2D dp table of m into n, similar way. Okay, now we'll first initialize this I will initialize with 0. Okay, next what we will do, we'll initialize dp 0 is equal to 1. Okay, because we already return 0 over here. So if we have encountered 1, or if we encountered a stone in the first position or the first cell itself, so as we did not encounter a stone in our first cell, so we can initialize dp 0 is equal to 1. Correct. Then we will first fill the rows. So so this particular cell is done. Okay, this particular cell is done, so we have initialized with 1. Okay, now we need to fill the first rows. So this row we need to fill, this column we need to fill, then we'll move to the next cells. Okay, starting is equal to I is equal to 1 and j is equal to 1. Okay, so first we will fill the first column. Okay, and then we'll fill the first row. So let's fill the first column, fill first column. Okay, in that case we will take a loop for I is equal to 1, I less than m, I plus plus. Okay, dp of I0 is equal to, if we got a stone, then in that case it will be 0. So obstacle grid I0 is equal to 1, then it will be 0. Else we need to refer whatever we got in our previous step. So it will be dp of I minus 1 comma I minus 1 0. Okay, so this is done. First column is done. Okay, next we will go for the first row. So this part is done. We need to go for this part. Okay, this part. Okay, so then we will fill the first row. Okay, so in this case for j is equal to 1, j less than n, j plus plus. Okay, dp of 0j. Okay, 0j is equal to, again if we got a obstacle grid, then it will be 0. So obstacle, if you get a stone in the obstacle grid, it will be 0. So obstacle grid 0j is equal to 1, then 0. Else we need to refer to the previous steps value. So whatever we have taken, whatever you stored previously. So in this case it will be dp of 0 j minus 1, right? So this is done. Okay, so first column we covered, and first cell we covered over here. Now we need to fill up these cells, these particular cells. Okay, so in this case it will be for I is equal to 1, I less than m, I plus plus. For j is equal to 1, j less than n, j plus plus. Okay, now if the obstacle, we get a stone in the obstacle gate at I and j position, then it will be 0 only. If we get a stone into the I and j position in the obstacle gate, so it will be 0 only. So in that case, if obstacle grid ij is equal to 1, if you get a stone, then dp of ij would be 0. Okay, else dp of ij is equal to dp of I minus 1j plus dp of I j minus 1. J minus 1. Okay, so this is closed, inner for loop closed, outer for loop closed. Okay, and then if we return dp of m minus 1, n minus 1, then we'll get the number of paths to reach the destination. Okay, and what is the time complexity for this? Time complexity would be, we are running 2 for loops, so m into n. Okay, space complexity would be m into n only, because we are taking a 2D DP table of size m into n. Okay, and there is no auxiliary stack space, so we remove the auxiliary stack space over here. Okay.